Okay, we're back. Nobody breathe. Love technology. All right. So let's get started and finish up chapter 2 here. So I just want to give a quick tour of their periodic table, so we're almost finished looking at our different elements. So we had left off on the halogens here. So the halogens are all group 7. And so these are pretty nasty, so let's look at fluorine. So fluorine is a gas. Here it is condensed at a low temperature, so it kind of looks like a yellow liquid. Otherwise, if you were using fluorine gas, it comes in like a cylinder. Pretty corrosive though, so you have to use like special regulators and all that fun stuff. But there's a lot of fluorine chemistry that people like to do where they try to fluorinate things. And fluorine is also really important, like being able to fluorinate things. That's good for medicine. So used a lot in like antidepressants, for example, have fluorine groups on them that helps them cross the blood-brain barrier as well. So I'm moving down. Chlorine is also a gas, so pretty nasty to work with as well. You can also generate chlorine gas. And again, here's chlorine. And so don't forget, these are also your diatomics, so fluorine, chlorine. So now let's look at bromine. So bromine is a favorable reagent for like organic chemistry. A lot of it just deals with because of the nature now. So now it's a liquid, so you can pipette it into your reaction. It is nice and fuming though, so it is like a red fuming liquid, nice and reactive, so you can brominate it or use it to brominate substances, and that's good for doing all sorts of organic reactions. And then moving down, iodine, which you'll get a chance to look at some iodine in one of the labs. I think it's like 3 or 4, where you get like a tour of the elements. And iodine's really pretty, and that it's like this dark silver violet looking solid. And this is also nice. And then what's cool about iodine is it'll sublime. So if you have a little jar of it, it'll like recrystallize at the top and make all these pretty crystals. And then so they do use iodine as a disinfectant. So you probably, like, I don't know if you probably had like a procedure at some point at a hospital, they swab you with iodine. So that's what they use. Just obviously a solution of it and dilute. And so there's astenine, so not particularly known. So apparently this is a short-lived isotope. So, and then so last, let's look at the. Let me turn off the lights in here. Yeah, can't use some contrast.
Oh, I meant putting on my glasses.
Oh, that also would help. And then so last over here are noble gases. And so they're called noble gases since they're generally unreactive. And so we have helium over here starting off the noble gases. And obviously you can guess that they are all gases. So you'll have a fun opportunity. Again, I can't remember which lab now, but we have a bunch of tubes. I'm like really proud of like the tubes that RCC has, because I actually haven't seen like as many tubes as we have and all the different places that I've been. But what you can do is you can put this gas in a tube here, and then you apply electrical current, and that's how you get those neon lights or other colored lights. So you'll be able to look at that and see the different atomic absorption spectrum for these elements. So there's helium, and then neon. Of course, people are probably familiar with neon lights. And then going down, so argon, I believe there are some compounds of argon. So, of course, chemists want to do cool and exciting things, so even though we just said they don't really react, chemists will try to get them to react. There's argon, and then krypton. So krypton is pretty cool. Oh, so argon, by the way. So I don't know if you remember, I had mentioned how sometimes you do air-free chemistry and nitrogen. Well, if you're really rich and your compounds react with nitrogen, you use argon, and that is more expensive than nitrogen, but has the advantage in that it's heavier, so it kind of pushes out any advantageous oxygen looking around. So, and then let's go back. So xenon. So xenon is sometimes used by P chemists as like a carrier gas, since it's so large. And so if you were trying to lower the kinetic energy of something, kinetic energy is 1/2 mv squared, so you want to slow things down and use something of a heavier mass, like xenon. And then, of course, radon here is radioactive. And so any sort of radioactivity in your basement could be from the presence of radon. So radon just naturally off gases in like basements or caves, but small amounts, so nothing to worry about. All right, so that was kind of our descriptive tour of the periodic table. And then, so if you're in class, you snuck in, so make sure you get a copy. Of this handy dandy periodic table. And so I can also post a copy online, or if you're online and ever want to come in and get a nice cardstock version, definitely feel free. All right, so let's kind of take what I want to call a new tour of the periodic table. So now we want to look at the electronic structure and then start to understand, why the periodic table is in this funny order and why things react the way they do. So now let's look at this. And so we're starting here. And if you look on your periodic table, you have like different numbers on the side. So we have like number 1, 2, 3, 4, 5, 6, 7, etc. So we want to start here at hydrogen. And so on row 1 here, we're going to be filling up our s orbital first. And so let's actually highlight this. So this all over here, and this will make more sense as we kind of go along, but this is considered our s block. So that means they're valence electrons. And so let's define what a valence electron is. So a valence electron is just the electrons that occupy the outermost shell. And so for all of these elements, they have their valence electron will be in an s orbital. Again, this will all kind of make more sense as we go through it. And so let's start. And I'm also going to kind of do electron configuration at the same time. because they go hand in hand. But if we start with hydrogen, we can write that, so that electron would go in the 1s. So this indicates what orbital we're in. And then we put just a little 1 here, since hydrogen just has 1 electron, or at least neutral hydrogen, so 1 electron. Then what's kind of awkward is, so helium, right, is still part of the S block. It's just sitting over here for other reasons. And so this is 1s2 now for helium. We can add that to our electron configuration. And so why it's over here is because even though it only has 2 electrons, we still consider it to be basically fully occupied and satisfied. And so this follows what we call the duet rule. So have you guys heard of the octet rule before? So some people. So we use the octet rule to refer to like everything else, basically saying that they have the maximum number of electrons and they're happy, blah, blah, blah. But for helium, it's appropriate to say that it's satisfied by the duet rule. Since it has 2 electrons, it only has s orbitals. So that is what it's satisfied by. And so if we look, so now let's look at, well, you know, what is an s orbital? What does it look like? And so we have our s orbital here. So this is what it looks like, just a big sphere. And so every energy level has 1 s orbital. And then if we go up, so let me pull up that P table again. So why I like this P table is because it helps you with the electron configuration and then also visualizing all the orbitals. So if you go over to electrons here, now it gives, so it shows us, right, just our little 1s there. But what I want to show is, okay, so we filled up, we did hydrogen, we did helium, and you can see the electron configuration, right, 1s2 there. And then if we go down to lithium, so you can see, right, the 1s shell is still there, right in the middle, so now it's in the core. And then this blue color represents our 2s now. So this begins the 2s. And so each subsequent, let's go back. So each subsequent level then, right, keeps adding little onion rings, basically, of s orbitals. So if you look at sodium, I can't really zoom in on this, I don't think. Oh, maybe I can. Sometimes the zoom doesn't function. But you can tell with that sodium, so it still has that 1s, right, deep in the center. Then it also has a 2s, and we'll look at how to fill in all that stuff. And then we have our 3s now as our, again, outermost valence electrons. And then you can see that pattern, you know, repeated, just more and more onion shells. All right, so let's go back. So we were at lithium, so back to our S block. So lithium, just so we can follow the pattern of electron configuration. So 1s2, because we have to fill in the lowest energy levels first. And now we're at 2s1 for lithium. And that makes sense. So lithium has an atomic number of 3, so 3 electrons. Then beryllium, just continuing over. Now 1s2, 2s2. And so now, if we want to go from beryllium to boron, so now we need to add our next orbitals. And so let's highlight all this over here. So all these make up our P block now. So let's look at what our P block is. What does that mean? So our P block just means that we're filling in these P orbitals. And then so there's 3 of them. They go in the X direction, then Y, and then Z, and they are called degenerate. So these are degenerate, meaning that they all have the same energy level. And so notice there are 3 p orbitals. And then each one of these p orbitals can hold 2 electrons. All right, so you have these 3 p orbitals. And that is not how you fill them up. I just drew in the electrons. So that means there's 6 total that can fit in the p orbital. And so notice that this is 1, 2, 3, 4, 5, 6 across. So this can help you remember how many total electrons should go in the p. So you just count, okay, that's right, 6 across to match with the 6 electrons in my p block. So then we can continue with our electron configuration. So then boron would be 1s2, 2s2, and then 2, since we're still on the 2 level. And so that's another important thing. And I don't want to go into the quantum numbers or anything right now. But notice that the p starts right at level 2. So basically you cannot have like a p orbital in this one level here. And that goes into more math later. But so now we're at 2p1, so we start with 2 with our p. And then so we could just continue filling down the line. So let's do fluorine. So what's the electron configuration for fluorine? So looking in the chat, or you can start shouting it out in class. I heard 1s2, 2s2, and then how many p electrons does it have? So use your periodic tables. You got them in front of you. You can't. So you have to count. So you want to count from the boron. Yeah, so 5. So 1, 2, 3, 4, 5. So then 2p 5. And then, so let's just finish up. So looking at neon, so of course neon would have 1s2, 2s2, 2p6. And then let's take a look at neon for a second. So then these electrons, so again, these ones are going to be all in the outermost shell. So these would be considered its valence electrons. And then these 2 inner ones can be considered our core electrons. And so anytime we're looking at reactivity and how things react, we're always focusing on our valence electrons. All right, so then now, so we were at neon, so now we're back, row 3, so we can start, so now this is our 3s1, 3s2 for magnesium. And now things are starting to get kind of lengthy too with writing out these electron configurations. So we can write, 1s2, 2s2, 2p6, 3s2 for magnesium. But we could also write our kind of abbreviated electron configuration. And so how to do that is you want to find the previous noble gas. So you could use helium if you were looking at lithium. But since now we're at magnesium, the previous noble gas is neon. So we can just abbreviate it. If we write neon in brackets here, that's meaning, all right, take the electron configuration starting at neon, and then you can go from neon and then just start 3s2. So then you just write 3s2. So that makes things a little simpler. So let's go back to our tour. So now we start, so I would just write 2p. So now this starts our 3p. So what's our electron configuration? Let's do sulfur. So how would you write that electron configuration?
For sulfur specifically?
Yeah.
Let's see, so sulfur on the periodic table is there, so it would be 1s2, 2s2, 2p6, 3s2, and then 3p4.
So that looks good. Is that what other people got? So we could also write it in our abbreviated form. So again, starting at neon, so we just start at neon, then 3s2, and then 3p1, 2, 3, 4. And I see a yes in the chat. Thank you. Question?
So I noticed something really odd that happens with chromium, but also copper, silver, and gold, where instead of filling up the next for the D block for 3D4, it instead steals one from the fourth S block, making it so it's 1s2, 2s2, 2p2, 3s2, 3p6, but then 4s1, 3d5. Why does it do that?
So I didn't want to quite talk about this quite yet.
Oh, sorry.
It's like a little, let's hold that thought for like a
Okay.
little bit longer, because it's not going to make any sense if we haven't even talked about the D's. So let's get to the D's and then we'll go to the question.
Understood.
So we're continuing along so we can fill up. So this fills up our 3p6. And then this is where things start to get a little funny. So this is 4s1, 4s2. But now this is where the D's start. And the D's start at your energy level 3. So this is 3D, even though our main energy level is 4. So I would write that on your periodic table. So we'll go 3D. And then fill all this up. And so let's look at the D orbitals and see what that looks like. So there are 5 D orbitals. And so this is where things get, we'll start to address your question in like 1 second here.
Right on.
So typically, you consider that the D orbitals are degenerate. What you find is that that's not actually the case, and that those 5 D orbitals plus the 4s orbital can kind of swap around, and that's what you get in that case. And so we'll look at it in a second, but let's finish looking at these D orbitals. So there are 5 of them. For our purposes, again, we generally just consider them to be degenerate. Why we skip over the transition metals, though, is because, again, a bunch of funny things happen based off of the geometry. And these D orbitals take different energy levels, but again, that's beyond the scope of this class right now. But what we care about is that each one of these d orbitals can hold 2 electrons again. So that means that we have a total of 10 electrons that can be in our d orbitals. And again, I would highlight this area. So this is all our d block. And so it should be 10 across, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yay! So you can remember how many electrons go in there, and hopefully the number of orbitals, as long as you remember 2 electrons in each orbital. All right, so let's try to answer your question without hopefully getting too confused. So which element did you mention again?
Chromium, just because it was the first one I noticed it happened at.
So let's look at chromium, and
Sorry,
it's
chromium.
and so for this, so kind of for our purposes, I wouldn't expect you to get what like the true electron configuration is. So if we were going for the electron configuration of chromium, so let's start at argon to make our lives easy. So we have argon, and then 4s2, again, just filling it up how we would expect it to be. And then 3d, 1, 2, 3, 4. So 3d, 4. And so I don't expect you to realize anything beyond this, but what you are saying and what actually happens, and so now let's draw this out. So basically, we have our 4s, which is slightly lower in energy than these 1, 2, 3, 4, 5d orbitals. And so what happens is if you fill it up like this, so you fill up your lowest one first, then 1, 2, 3, 4. So it's not quite happy to have this empty orbital here. And then what we'll learn too as we fill in these electrons, so you pay a small energy price to pair them in the same orbital. And so it must actually be favorable to, again, do some kind of geometry distortion. And then instead, so now we have 4s, 1, 2, 3, 4, 5. And so it must take less energy to just go and give 1 in each orbital, including our d, even though, right, there's some energy gap here, but at this point, it's so insignificant that the distortion makes it so that it's more energetically favorable to fill it up like this. Yeah.
Okay, so basically what you're saying is the amount of energy that it takes to have two electrons in the same energy level of 4s is greater than, or at least equal to, the amount of energy it takes to bump 4s up to d3, right?
Exactly.
Okay, that makes better sense. Thank you.
Yeah, and like I said, the transition metals do this weird stuff all the time of like shuffling back and forth from the 4s to the d's, and you see that again once you start like doubling the numbers. But that's kind of, beyond what we're going for here in this like basic level. So if you see this, know that not to panic, you know why this is, but I'm also not going to mark you wrong for putting this answer, right? Because you're just filling it in how you would expect it to, and so I'm not expecting you to realize, oh yeah, it's, slightly more energetically favorable. So that will explain the discrepancies you see. And so let's actually see what our P table says. Oh, I guess I have to zoom out. Where? There we go. And so on the periodic table, on this one, so it does give the 4s1, 3d5. So if you see that, just, okay, I know why it's funny type of thing.
Does that happen with any other blocks or just the D block specifically?
Mainly just the D blocks. The Fs tend to be just more well-behaved since of where they are.
Okay.
But, I mean, there's also some oddities in the F, but for other reasons.
So what you're saying is there's not an exception except for when there is, but we probably won't come across that exceptions.
Yeah, and I'm not penalizing you for the exception.
Got it.
Like, and if it ever were to come up on an exam, it would be like, you know, you expect it to be this, but it's actually this, like explain why type of thing. All right, so let's go back to our kind of tour and how to fill this up. So again, this is where things get kind of funky. So we fill up our 3D10, and then I would, you know, write a note to yourself that now we're back to the 4 Ps over here. So then we can finish up the 4 Ps. So that rounds up krypton. Back to rubidium. So this is 5s1, 5s2. Yttrium is back to 4D. Fill that in. Indium starts our 5p. So xenon finishes it. And then this is where things can get funny again. So we have 6s1, 6s2. And then your whole lanthanides should be inserted here, except, so I think this periodic table is a little funny, and same as the one that I gave you. So let's go over how we can determine it's funny. But let's look at, so what is an f orbital? So these f orbitals have these funky shapes. There are 7 of them. Each one of these holds 2 electrons. So that means there's going to be 14 total electrons in our f orbitals. But now, let's look at our periodic table and count how many across our f block is according to this. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So if you have a periodic table that's 15 across, it's not like wrong per se, but this is where you can get funky answers. So some people would start this as 4F1, but I would leave this, so leave lanthanum in our 5D over here. And then I would, same with actinum. And then have cerium be our 4F1. And so notice the F block starts at 4. So that's also funny. And let's see, does our P table agree with that? So lanthanum, so yes, so it puts lanthanum as, so if we look at lanthanum, its electron configuration, last electron is 5D1. And so that's where things can get funny too. So you fill up your 5D1 and then continue. So if we look at cerium, according to this P table, right, it goes 5D1 and then starts filling up the F block. And then what's funny, so maybe I lied about there being other oddities. So if you look at the next element, presidium, for some reason that one is 4F3. But again, that would be one of those that I wouldn't penalize you for. So let's look at, let's just write it out so we're all on the same page. So we were looking at element 59 here. So I'll just say 2 possibilities. So the way I would do it personally is just going in order. So let's see, what was our previous noble gas? So what's our previous noble gas for this one? So that looks good. So xenon. So let's start at xenon to make our lives a little easier. So we start at xenon. And then I would just fill up, so 6s2. Then we can do 1 for our 5d1. And then this would make it 4f1, 2. So that's fine. You know, that's again what we kind of expect versus apparently the actual, which is 4f3. And thanks, chat, too. I see that you are following along. And so the important thing, too, is being able to kind of check yourself at the end and kind of like, do I have at least the right number of electrons? Because that's what really counts. And so to check ourselves, you can just add the subscripts plus however many electrons you started with in, you know, xenon, if you're using the abbreviated notation. And so let me pull out my calculator for this, because I'm feeling lazy. And so we can see it too, visually. Oops. What did I just do? I did not mean to do whatever I did. There we go. So we're starting at xenon, so that's 54. And since it's neutral, right, we're just starting 54 electrons then. And then, so let's go back to our electron configuration here. So let's just add up this first one. So we have 2 electrons, so in our S, so plus 2, plus 1, plus 2. So again, just adding my little superscripts together. And that should give you your proper number, your proper atomic number, which corresponds to the appropriate number of electrons. So we can look, okay, we got 59, just like we were looking for. So that's a good way to double check yourself. And so let's kind of round this out then. So fill up all the F's.
Wait, but we own triadesium. How is that pronounced? 59, 59?
Yeah, I think it's praseodymium or something.
Because you had 2. You wrote it as 6s2, 4f3, right?
I wrote it as both. So again, I would expect you to do it like this just because that's how we're learning it.
Okay.
But the actual is 4f3. But again, there's kind of some discrepancy there and things get odd.
Okay.
So I care more that at least your total number of electrons is correct, right? And then you didn't do anything crazy like put like 2f2 or something, right? Because there's no 2f. That's not a possibility. So as long as it's reasonably valid. And then, so let's continue filling this up. So we would fill up, so our last one is lutetium or something, lutetium over here. So this finishes your 4F14. Now we can go back to hafnium, right? So now this is 5D2, etc. So fill all that in, or at least how we expect it. Now thallium, that goes back to 6P. And we can finish that. So radon, it finishes out our 6P. Now we're almost to the end here. So now this is 7S1, 7S2. Now we have the same sort of thing, right? Where our actinium can start off our 61, and then thorium is 5F1. At least, again, how we expected, so we can look at the P table to see how it actually compares. So actinium follows that nice 61. Oh, that's funny. So according to this, thorium is 62. But again, how would you know that unless you looked it up? So I don't expect you to know that. And then for some reason, protactinium goes back to 61,5F2. So you kind of get the point that they're all over the place. And then uranium follows the pattern nicely. So the rest of them seem to follow nicely, except for plutonium. Now it's randomly back to 5F6. But yeah, we'd have to look more into like the structure and everything too, and how it bonds to understand.
No, the F
Exactly.
block totally behaves.
Yeah, it does tend to behave though better than the D block. Yeah, so you can treat like the F block. It's more predictable than the D block synthetically. And then, oh, rounding out, so blah, blah, blah. Lawrencium finishes off our 5F14. And then, of course, all these unknown elements and new elements would be in our 7P. And then you could keep going on, you know, forever and ever theoretically, but we will end there. And then, so this is just another representation, basically, of what we did. And so this is the same order as this. And so this just shows you the energy levels. So if you notice, there's the greatest difference from like the lowest ones. So like the 1 to 2 has the greatest difference. And then that difference in energy level gets a little smaller as you go 2s to 2p. And notice this 2 to 3 is smaller, right, than the 1 to 2. And then they all get subsequently smaller and smaller and smaller. So that also explains why there's funniness, you know, towards the D's and F's. So let's do a practice. So let's see, which element do I want to do? So see if you can do the electron configuration for, let's do germanium. So take a minute or two, give everyone a chance to do it, looking in the chat too for answers. And we'll just make sure we're all on the same page. I can always display a periodic table. So do we have an answer? Looking in the chat too for answers. How are we doing in class? So where can we start? I see an answer in the chat that I like. So we're looking at germanium, right? So then what noble gas can we start with to make our lives easier? So argon, exactly. So then we go from, so starting at argon, and then what's our electron configuration? And we could go back, let's go back to this periodic table that's all marked up. So argon, and then what does this start?
4s.
Exactly, so 4s2, right? Fill that up. And then, so what's this next one? Go back to this one. Sorry? 4p. So germanium is part of the 4p, right? But then what do we have to fill in first? So all this block here. Except is it 4D? Yeah. So remember, that's why, mark it with a big 3D here so you know where to start at. So then 3D10, and then this goes back to 4P, so 4P1, 2. Let's do another practice. Pick another element. Let's see. Let's try palladium. And we might get different answers, but we'll see. What do we think about palladium? I see slowly becoming more lost in the chat. That's not good. Ask questions. What are we lost about? And also, like, the first part of chemistry, I think, is always the hardest, especially if you've never seen it before, because there's all these, like, symbols and funky stuff going on. And you have this periodic table that kind of tells you everything, but if you don't know how to read it, then it's kind of a lot. So just stick with it. And so question in the chat, so will we have the marked up table on tests? So I would suggest, so you can use this on a test. So tests I think are open book, is what I've decided. And so what I would do is make this, right, your handy cheat sheet. So that's why I'm kind of going through the whole point and annotating this with you so you can use it, right? Because that's the whole point of your periodic table, is it's supposed to tell you everything, right? You just look at it, and then it can remind you of everything. And if you want, multiple copies too, so you can have like different cheat sheets, like I will print out more copies. And then if you're at home, just print out whatever periodic table you like, mark it up, annotate it. I always suggest like write your formulas too on your cheat sheet, anything handy that you need. Yeah, and then if you have OneNote too, you could also, annotate it on here if you're fancy. All right, so we have answer in the chat. How are we doing in person with our palladium? All right, let's hear it. What do we get for our expected electron configuration? Yeah, I like it. So krypton. And then what comes next? 5s2. Yep. Oops, I don't know why I wrote my S backwards. And then 5s2. What comes after? 48. Exactly. And I think palladium is one of those funky ones that probably wants to do 5d10. If we were to consult this, or not, excuse me, 4d10. But again, I wouldn't expect you to know that. I'll just kind of put in parentheses actual. So this is totally appropriate. I just want to make that clear. Like, that's a good answer. That's what I expect. You're just filling it along. We don't know all these exceptions. So let's kind of take another tour of this periodic table and try to break things down a little better. So you have all these little numbers up top, right? 1, 2, and then we'll kind of ignore these, but then they go back. So I would look at these little numbers, so 3, 4, 5, 6, 7, 8. And so those correspond to the number of valence electrons. And if you want to write that, on your periodic table too, just again, go for it. So this says 1 valence electron, right? So everything in this first row here has 1 valence electron. Again, we kind of said that from our shells. So that was 1s1, 2s1, 3s1, 4s1, 5s1. Oh my gosh. I have a problem with S's and 2's today for some reason. Brain's misfiring. 6s1, 7s1, right? So you get the point. But now this is also telling us a bunch of other things too. So if we go back, right, I did our tour of our periodic table. We said that these were all extremely water reactive. So why that is because of its electronic structure here. So it can easily lose that electron. So let's start throwing in a couple of other things. So we can also write what's called its Lewis dot structure, or electron dot structure. And so all that is essentially translating these electron configurations, so being able to take this, and then can we kind of make a little picture of it? And so what I mean by that is, so we have, again, our first row, they all have 1 valence electron. So this is for alkali metals. one valence electron. And so we can write that just like that, just depict it like that. And then, so in this case, it doesn't really matter what side I put the electron on. We can do it with sodium too. And so again, we're just depicting our valence or outermost electron. So for all of those, right, they're just going to have one dot. So we can do potassium too, little one dot, and it doesn't matter what side. And then, so if you look on your periodic table, and so this one doesn't have it. Let me see if I can find one online. If I could find the same one, that would be cool. I can never find this one. Ah, I actually found it. So let me post this in the chat for those of you online. Oh my gosh, too many windows now. So this is the one I like. So let me bring it over to this one so we're all on the same page. So why I like it is because it has this thing called oxidation states on there. And so what I care about is, so notice it has this little +1 charge here, and all these. I'm kind of ignoring hydrogen because you notice hydrogen also has a negative charge, but it can be a hydride. But right now, I just want to focus on that +1 charge. And so this oxidation state just means kind of what does it tend to do when it forms compounds. And so with lithium having this little +1 charge, that means that it tends to lose an electron when it forms a compound. So if we go back to our electron dot structure, we can kind of see why that would be the case, right? That one electron, it's really reactive, so it's just going to pop off. And then so we could make lithium +1 species. And so now let's look at kind of this. So what I do, I post all the notes on Blackboard, so yeah, I will post. They're always exported after class, so you can get all the notes. And I export it as both a OneNote and a PDF. And so now we can look at this. And so this is kind of related to your homework. So now we can determine, so let's do number of protons, number of neutrons, and number of electrons. So this lithium +1 species, so how many protons does lithium have?
3.
So 3, so we just get that from our periodic table. So element 3. I guess, so let me give you some more information. So how many neutrons does it have?
Round 4? Possibly 3? That's
Well, I gave you some more info so we could pick an isotope of lithium.
oh, okay, then 4.
So 4 neutrons, assuming that it's lithium-7. And then how many electrons does this species have? So I see fingers for 2, fingers for 2. So excellent. So this would be 2 electrons. I see it in the chat too. So excellent. And so with the charges, how they work, there's a couple of ways to think about it. So of course, you know, protons are positive, electrons are negative. So you have a positive charge, you know you've lost an electron. Or you could formally kind of write it. And the way I think about it is you have, so your number of protons plus, I put like the negative number of electrons. So it's basically minus the number of electrons, but I just kind of think of it as, yeah, minus the electrons. Since electrons are negative, you can think of it as adding electrons, but just remember that electrons are negative. So whichever way kind of works. And so that should equal, right, your total charge. So of course, in this case, just filling in the math formally. So 3 minus our 2 electrons, of course, leaves us with a 1 plus charge. So now let's go back and keep looking at our Lewis dot structures. So that means our alkali metals then, or alkali earth metals. So they all have a 2, right? So these all now have 2 valence electrons. We saw that from our electron configuration, right? That now this is 2s2, 3s2, 4s2, etc., etc. And so we could write our Lewis dot structure. Alkali, earth. And so the way I would do this, so we have magnesium. And so we want to base it off our electron configuration. So if we're looking at magnesium, so first of all, what's magnesium's electron configuration? What did you say? So looking at electron configurations, remember that's like the 1s2, 2s2, blah, blah, blah. So 3s2 is the valence electron, and then we just want to fill in, so 1s2, 2s2, 2p6, right? And you can double check yourself, so I see it in the chat, and then just double check yourself, right? Add our superscript, so 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, and does that give us the right number? So yes, indeed, so 12, so good job. And then again, we only care about, right, our valence electrons. And then so this is where I'm slightly picky, and you'll see textbooks do things that I would consider erroneous, at least for kind of our purposes. But you want to write your Lewis dot structure to reflect that. And so that means that I would put these 2 electrons in the same orbital. So I'd put them on the same side there. So kind of one way to think about these. And it doesn't matter which one you assign as what, but this is basically an s orbital, and then you have your 3 p's. So this can be p. And I'm just calling this, right, px, py, pz. Doesn't matter who's who on what side. I'm just kind of trying to relate it that we have 4 sides, 4 orbitals that we're mainly looking at to fill up. And so that's how we can relate those. And if I know it's a lot of information, but if you can kind of synthesize this all together, this will really be helpful for everything. Yeah.
So I know that there's a different structure or like way to visualize the electrons
Yeah.
Is that also, what, I don't remember what that one's called.
So that one, so we can look at that, and actually it's a good way to segue into some things. And so if you learn kind of this, we'll say elementary school, so let's look at Krypton, just because Krypton's a good one to show all of this. And so you might have learned in school, right, you have like your first circle, and that has 2 electrons, right? And then you have your second circle, and that has 8, right? And so where this comes from is we can relate it back to the periodic table here. Oops, wrong periodic table. So we start with our 1s, so that makes sense, right, for those 2 electrons. And then this second shell, so basically these are different shells, so this is n equals 1, n equals 2 now. So at the n equals 2 level, now we have, right, our s plus our 2p, so that gives us 8 total. So that's where that 8 comes in. And then, right, the next one is now our n equals 3 level. And usually they say, right, there's 18 electrons. And so with that one, you can see where the 18 electrons comes from. Since we have 2 from our S, 6 from our P, so now we're at 8, and then 3D, so now that's 10 more to give us 18. And then we could continue on. And now I have to do some math to myself because I don't remember. So then continuing on, so n equals 4, right? And so, so if we're at 18 for the D, then we add plus 14, since now the n equals 4 contains F. And so that gives you 32 total. So that's where all that comes from. I just don't like it because this is just like this simple onion ring model, which is, I mean, it has its uses, it has its appropriateness, but it just doesn't go into like, you know, the subdivisions of S's and D's and P's. But it is a good understanding, so this is just our simple Bohr model is what it's called. And so it at least gives you like the shell structure and the appropriate number of electrons, but yeah, not as deep as we're hoping to go. Yeah, good question. And then you had a question?
Yeah, when we were doing the configuration, is it always like the last one? Is that our valence electrons?
Yeah, it's always the last ones. And so that's kind of why we ignore the D's, because that gets weird. But like the last ones for these are always going to be like your D blocks and sometimes a 4s. But then let's say we were looking at selenium, for example. For those valence electrons, we would mainly just look at the 4s and the 4p as its like valence. And then we just kind of ignore the D's. Because in reality, these D's don't do any bonding with compounds of like these, if that makes sense.
Okay, so you add the S with the D to get the valence.
Yeah. And so that matches with this number up here. So we're still kind of going through it slowly. Yeah, so that's why I would write it like this. And then so let's try to answer some more questions. So we look at, let's just look at boron or group 3. Sorry, I'm all over the place with my periodic tables. So now, right, this has 3 valence electrons. 4, 5, 6, 7, 8. So either, again, highlight those numbers to kind of trigger you, or you can see there. And then so let's look at how we would write our Lewis dot structure for boron. So for group 3, there's actually kind of two ways to write this. So boron, again, I would do this kind of based off of its electron configuration. So if we do its electron configuration, 1s2, 2s2, 2p1, and then we're looking at our valence electrons. And so I would write its Lewis dot structure like that to reflect it. But what's also kind of funny, and I probably couldn't mark you wrong, is so boron likes to make 3 bonds. So if you kind of wrote something like a hybridized structure like that, this would be okay too. But we'll kind of go more into that. And then so looking at other exceptions, so now group 4. So we have some general structure, XS2, XP2. And so for most of these, like silicon and germanium, I would draw its Lewis dot structure to reflect that. And so what you would write is 2 electrons in the S, and then what's funny about the P, so let's actually draw it another way for a second. So we have our S orbitals and then our 3 Ps. So when we go in to fill in our electrons, we want to start, again, fill in the lowest energy first, but then we don't want to pair anybody unless we have to, right? So then 1, 2, so we have 1 empty p orbital, so I would write our Lewis dot structure to represent that. And you can write it like that, doesn't really matter. But this does reflect the nature of silicon and germanium. So they are available as a species like this, so you can make like germanium dioxane, so they are 2 coordinate and then can bond to something with these 2 electrons. But then your exception, so let's write a big star, is carbon. Right, so we went on and on and on how carbon is a whole fundamental building block of life. And so because of this, carbon always makes 4 bonds. And so we want to draw our Lewis dot structure to reflect that. And so we draw carbon with 1 dot on each side to show that it likes to hybridize. And we'll go into more of what that means exactly with the term hybridization, but just know that carbon, 4 bonds, so 4 dots, or 1 dot on each side. And then, so just looking at some other things that I want to point out as we look at our periodic table and make our way across. So looking at the oxidation states, so with our group 3, right, those will have a +3 oxidation state. So that means, right, they want to lose those electrons, so they tend to lose their valence electrons and become positively charged. But then group 4 is where you kind of have this switch, and you can see that reflected in the funky oxidation state. So if you look at silicon, it has a +4 and a -4, and that makes sense, right? Because it's right in the middle, so it could either lose 4 electrons, and go back to this noble gas configuration, or it can gain 4 and become the other noble gas configuration. So it can go either way. It just kind of depends on the formalities, whether it's gaining or losing electrons there. So now let's look at nitrogen, or group 5, what those Lewis dot structures look like. So group 5, so again, they're all XS2, XP3. And so we, again, want to draw our little picture to represent that. So we have 2 in the S, so I'll put 2 on the same side. And then we want to fill in our P's. Again, 1 in each P before we start pairing. And I'll draw this the other way just so we can see. So you want to be comfortable, seeing this in a bunch of different representations. 1, 2, 3. I think there's also like a box form that you see in textbooks. It's like S, P, and so that would mean the same thing. So your 1 box for your S orbital, 3 boxes for your P. So just kind of get used to seeing it like that. And again, we can write it, any which way, doesn't really matter. So phosphorus, let's do arsenic just for fun. So all those are appropriate. And then if you start looking again at your periodic table, so now these are just 3 away. So 1, 2, 3 from noble gas configuration. And so they tend to be in the -3 oxidation state. They have +5 on there too because they can make a bunch of compounds, so they can be formally +5. But let's do a little practice here now. So if we have 32P, 3-, so take a minute, so figure out protons, neutrons, and electrons. So I'll give everyone kind of a minute to stare at that or so. So answer in the chat looks a little funny if that's protons, neutrons, electrons. So double check that. You have an answer in class? So how many protons does this have? 15. So 15 protons. So don't forget, this is your atomic number, so it should be there. Double check it on your periodic table. And then, so how many neutrons do we have? 17, excellent. I see chat's also on top of it. And then how many electrons? 18, excellent. And I see chat also has that as well. All right, good job. So let's finish off here. So just to kind of round it out, so group 6 now, those were our smelly ones. And so that has a configuration, right, XS2, XP4 now. So 2, 1, 2, 3. So now we have to go back and pair 1. And so just draw that to represent it. Again, we can represent it like that. And then group 7, I forgot lecture lens at 6:20, doesn't it? I was going to 6:30 in my mind. So group 7 would just look like that. Oh no. And then group 8, of course, would have a complete shell. All right, we didn't quite get to what I wanted to get to because I was saving 10 minutes accidentally. Because I forgot that you need to know some trends. So I'm going to quickly give you periodic trends. I know we're like over time. I apologize, but I at least want to quickly go over this so you can do your homework. And then we'll probably re-explain why on Tuesday. And so we find that our radius, so we have decreasing radius as we go across the periodic table. So we'll go over why, but basically you're still in the same shell, but filling in electrons, and you have those more electrons in the same shell, so it'll bring it closer together. But of course your radius increases as you go down. And then you also need to know ionization energy. And so ionization energy, so that's ionization energy. It's basically energy needed to remove an electron. And so that increases as you go across because you're filling up your shell. So that increases as you go across. So obviously fluorine would not want to give it an electron compared to lithium. But then ionization energy decreases as you go down as the shells get larger, so they're farther away from the nucleus, so easier to kick off. All right, I apologize, we're over time. And so we'll go back over trends and look more in detail on Tuesday and then continue on with whatever chapter is next. So thank you all for your time as I go on and on. So I will see you Tuesday. And yeah, if you have stuff for me, I will take it. And then I'll hang around on stream in case there are any questions. And then the best thing too is just to make individual appointments. I know that we had kind of said that maybe like an online recitation day. I haven't gotten feedback or set a time, but y'all are all together in the chat now. So if there's like a convenient time, especially Wednesdays or Fridays, I'm really free. Otherwise, I'm more than happy to meet with people individually. Oh, questions? Yeah, so that looks good, that looks good, that looks good. 92. And then, yeah, 92. 11, 12, 10, perfect. 16, 16, 18. Yep, that looks all good there. So I see Friday evenings, maybe, for people. And then Black Sage, I don't know if you're still in the chat or not on YouTube. I was just going to say that all the lab videos are online. So it's fine if you haven't done the lab. We just had in-person lab. Okay, perfect. So you're there. So yeah, so the video is online. Give me 1 second and I can show you. Just all over the place. So if you look under content, and then I posted it in the week 1, so there is no lab on week 1, it's just there in the week 1, and then lab. So the lab PDF is here. Yes, so you're doing labs at home. There's like still a few spots in lab if anyone wanted to join, but lab is like Tuesday 7 to 10, so I know it's not the best time. But yeah, so you have the paper here, and then there's a link to a video. And so this is all the previous instructor. But it goes through, so you click on here, and it just goes through the different parts. So you don't have to buy any materials or buy anything. You just kind of watch the videos and follow along, and everything, all the data you should be able to obtain from the video. So you don't need to buy anything. Yeah, and that's why the videos are like not me, but I wasn't about to retape everything again. But yeah, all that's there. So the first lab is due on Monday, and I just have the Turning Through Gradescope. Yeah, perfect. So you have that downloaded, and then I was just asking people to turn it in through Gradescope. So I don't know if you've gotten a second to look at that. Yeah, and then so I already have the assignment up there, so you just have to turn it in, and that just makes it easier for me so I can grade everybody consistently and fairly, on perfect. So pin, so you're ready to go. Awesome. So I think that's basically all you need to know. And then everything else, everything's just posted. Sorry, I lost my window. There it is. So everything, just posted in Blackboard. So content, week by week. So week 1, the assignments that were due this past Monday are here. And it's fine if you're behind, like I accept late work, all good. And then I also post my notes here for lectures. And then, yes, so recitation, you don't have to do anything for recitation, but you have to at least be signed up for a section as part of the entire 5-credit Chem 104 package. And so in the announcements, there should be codes here. I don't know if these registration codes are still valid. They may have expired, but just send me another email, and then I can forward that to the registrar and get you registered if you're not officially in a section. But yes, everyone needs to at least be registered. Again, it's no extra work. You don't have to really do anything for it. Recitation is just like a study hall kind of period. And then all the videos, I try to make it easier, I hope, and that they're just on my YouTube page. Yeah, so if it still allows you to sign up for classes, then yeah, exactly, you can sign up. And then I have the other lectures there, so you can, catch up and watch them or watch them again. And the nice thing about posting them on YouTube is you don't have to wait for me to upload them or anything. They're just available as soon as I'm done. Any other questions? I'm glad you were able to come live so we could clarify some things. I know things can be confusing with these distance classes. All right, sounds perfect. If there are no other questions, I'll probably end the stream. Just gonna give it some time, so I'll take another questions for another minute or so. And thanks again for watching. Thanks for the precipitation. Oh, last question. Yep, still here. Yes, this is an intro to chem class, so I'm assuming that you have zero knowledge about chemistry and, you know, basic math skills. Yeah, exactly. So you've never taken it before. Yeah, and if you're completely lost, again, just stick with it because the beginning chemistry is always the hardest. Trying to learn all these crazy symbols that chemists have and all these dots and electrons and what the heck of it is saying. It's like almost a new language, really. Like, treat it like a new language, right? You just got to get used to all the things. Yeah, exactly. And we can always meet individually. So if you go through the videos and you still kind of feel like I don't know what's going on, we can chat and figure out. All right, nice to meet you, Simon. All right, you too. I'll give people another minute or so in case anyone else has any questions or wants to say anything. Then I will end the stream. All right, thanks again, everybody. Excellent class. Thank you again for your participation. Y'all in the chat, make this happen. It's great. Thank you, those who are watching after. I really appreciate everybody and everyone's hard work. Again, just email me if you have any questions. I'm going to be signing off now.